Alright, what the heck are we doing today? We're talking about lab 3, we're talking about lab 4, we're looking for lab partners. So, there's someone in here who's working in a lab group of 1, they're looking for a group to join. So if you have only 2 people in your group, right, and you want a third person in, which is always handy, hop onto the discussion area of Canvas, and there's a note from the student asking for a group.
I already got someone.
You already got someone? Okay, cancel that. Rewind. Cool. All right, questions on Lab 4? I got lots of questions over the weekend and yesterday and today. Kind of makes sense in the end. So I'm assuming everybody went with the half adder, full adder design instead of implementing the full truth table, right? Okay, good. All right, well, so we need to go over lab 5, which I'm going to wait and do after the break. And you probably want to talk about the midterm, right? Okay, let's talk about the midterm. So I posted this on Canvas already. This was a general list of topics. And this is just basically what we've been doing, right? So the idea of digital versus analog, right? So ones and zeros, 2 voltage levels, high and low, and so on. Binary numbers, right? So we usually use weighted positional notation. We have this thing called 2's complement, which has no impact on positive numbers, but it lets us write negative numbers by taking the positive number, complementing and adding 1. Right, so it's a way to represent negative numbers in binary. There's also signed magnitude, where you just put a minus sign in front of your number, right? So if you have 7 is 111, you could write minus 7 as 111 with a 1 in front of it, right? And that's a different way to represent negative numbers. We could come up with a totally random set of mappings between bit patterns and positive and negative numbers, right? There's nothing that says you have to use weighted positional notation, you have to use 2's complement. There's lots of different ways to do this, but usually we use 2's complement, okay? And that's pretty much all the encoding that we've done so far for turning integers into binary things. So range of numbers, what's the largest, smallest number you can represent? We've seen questions on that. Converting between decimal, binary, hexadecimal, and octal, okay? So mostly you want to know how to go between decimal and binary, binary to decimal. But if you have a binary number, you can convert to octal by putting in groups of 3. If you want to go to hex, you can break it into groups of 4. If you have a hex number, you just write 4 bits for each digit. If you have an octal number, you write 3 bits for each digit. Right? So octal, hex, binary, those conversions are straightforward. The trickier one is from decimal to binary, or back from binary to decimal. And that's the repeated divide by 2, take the remainder, that kind of thing. And we can have things on the right side of the decimal point, right? And those are just negative powers of 2, so 2 to the minus 1, 2 to the minus 2, and so on. And you've done questions like that. We can represent characters in binary, that's what the ASCII code is, right? You don't need to memorize ASCII codes. Just know that ASCII is a way to take a group of bits and say this is character A, this is character X, or whatever, right? We can add and subtract in binary, and we can do this the way we do pencil and paper, addition or subtraction, where we add and we ripple the carryover, or we subtract and we borrow. But we can also subtract in binary by adding negatives. So A plus B is the same as, A minus B is the same as A plus minus B. And minus B is just B's written with all the bits toggled plus 1. So we can do subtraction. That was kind of it for binary stuff. Switches and LEDs, so still a perfect record on labs of switches hooked up correctly. So that's good. So you'll be wiring up some switches and LEDs. Make sure you use a 1K ohm in series with LEDs so you don't burn them out. LEDs are oriented. Logic gates and or NAND NOR XOR XNOR and NOT. Right, those are your basic gates. You should know what the symbols are for them, what they do. You should be able to write a truth table for them. And then the general goal is to go from a truth table to an equation to a circuit, or from a circuit to a truth table to an equation. Actually, probably go from a circuit to an equation to a truth table. If you want to put them in the right order. It's the reverse of the one before. Yes?
You're saying we're going to be implementing these like for the midterm, like with physical things?
No.
Just paper?
But just on paper.
All of it.
So I could give you something like right, and I could ask you to write an equation for x in terms of a and b, and then to sketch a circuit that implements that. Or I could give you something like this. And I could ask you to write an equation for x in terms of a, b, and c, and write a truth table from that, or things to that effect. So that process of going back and forth between those different versions of a circuit. Theorem proving, so proving De Morgan's theorem, for example. Yes?
If we're going from a circuit to an equation, are you going to want the simplified equation? Or
I'll let you know.
okay.
So if I ask you to do this, my suggestion is first write the unsimplified version, which would be what? X equals, well, it's an OR, so it's something ORed with something else, right? This thing is C, this thing is a NAND, so it's A, B, bar, and nobody can tell you that's wrong. Okay, so I would definitely start with that. But then if I'm ask you to simplify it or ask you to do something with it and simplifying helps, go ahead and simplify it if possible. But I would always start with like a direct translation from here to an equation. Because if you get this wrong, everything else is going to be wrong, right? But if I see this, I say, oh, you thought that was an XOR instead of an OR, and I can take everything else and give you credit for that if that's done correctly.
See, I gotta do that part right, but I need the simplification.
Yeah, simplification is a challenge in itself, right? So that's another reason to have this down. Because if you simplify and the simplification's wrong, well, at least you did the conversion from a circuit to equations correctly. So it's largely about partial credit. Theorem proving, so we can prove things either algebraically using these rules like De Morgan's theorem and adjacency and so on, or we can prove things with truth tables. Right, those are the two most direct ways to prove that, you know, AB or AB bar is equal to A. Right, that's the adjacency theorem. So playing around with those things. Sum of products, products of sums, we've been working with those extensively. So if you have a truth table, you should be able to write an SOP or a POS representation of the output. Remember, you don't negate things just because you're using a POS or an SOP. A truth table is a truth table. It never changes. These are different ways to write a given truth table. But if I wanted to write this truth table using sum of products, I would say x equals sum 1 comma 3, which is A bar B or AB. Right, so I look for the ones and I add those min terms. If I'm writing a product of sums, I look for the zeros and I write those max terms. So this is A or B, and max term 2 is A bar or B. But don't do this thing that I saw on some homeworks where you start negating this to do a different representation. This is the truth table we're trying to represent. Right, so X should be exactly one of those. Yeah?
Do we need both when we're answering that? Do we need the sum of products in both forms, or one or the other is fine?
Unless I ask for it in compact form, you should always spell it out.
Okay.
Okay, but this is called compact form. But don't use that as your only answer unless it says write it in compact form, or compact form is allowed, or something like that. It's not bad to put down while you're working through it, but go ahead and expand it out, because usually I want to see the longer version of this.
Okay.
Oh, so you might have seen this on one of the homeworks. Sometimes you'll see something like this. This mysterious MD parentheses 247, those are don't cares. So it means in rows 2, 4, and 7 of the truth table, there's a dash. So we want min terms 1 and 3, and we don't care about terms 2, 4, and 7. So those are dashes, and that helps you with your K-map simplification. So that's just a piece of terminology or symbology. So MDs, don't cares. Remember, don't terms you can optionally cover in K-maps. So min terms and max terms. Minimization, you can minimize algebraically by trying to factor things out and stuff, but the easier way is to use a K-map. So you've done tons of K-maps at this point. You're basically covering ones if your goal is to write a sum of products. You're covering zeros if your goal is a product of sums. Wrap around on the edges, take advantage of don't cares, and if you have a checkerboard, play around with some exclusive ORs and see if that'll give you the expression that you're looking for. Otherwise, if you've got checkerboards, you're just going to get really big expressions for each 1 or 0 that you cover. You should know that NANDs and NORs are complete, so you can build any logic gate out of just NANDs or out of just NORs, and we've played with that a few times. Most recent homework, multiplexers, demultiplexers, 7447 you're playing with on your lab. Now, I'm not asking you to memorize how to use a 7447, right? But it's an example of something that takes one version of input, in this case 4 bits, and gives you a different version of output, in this case 7 bits that drive a 7-segment display. Okay, so that's a general notion of an encoder or a decoder. It's changing from one coding to another. Priority encoder is another version of that, and again, I'm not going to ask you to know, the pins or the part number of a priority encoder. It's just something we've talked about along the lines of these sort of medium scale chips. So multiplexers and demultiplexers you should know more about, right? So multiplexers let you take multiple inputs and select one to go to the output. Demultiplexers go the other way. And you can build multiplexers out of other multiplexers. You can build arbitrary logic out of multiplexers. And there's other things we've said about them. PAL, PLAs, and PROMs, so programmable logic devices. And we've talked with those, and you've got a homework question on those. And fuse maps are just the AND plane or the OR plane, right? So did I assign those questions for today? No? Okay, so there were homework questions on that that I said not to do last week because we hadn't got to them, but we've gotten to them now. I was hoping to have you do those, but I think I forgot to tell you that. Okay, we'll adapt. And then half adders and full adders. So you've been playing with that in your lab, right? So you should know about those things. All right, so questions about this? So you've got a list of topics. It's basically the first 3 chapters of the text plus chapter 9, right? And you can go home and you can spend the next 2 days worrying about which of those things are going to be on the midterm and trying to study the ones that you think are most likely or worth the most points. And that's not really my goal here. So I'm going to show you your midterm. So I've left out the specifics, but this will be your midterm on Thursday. Question 1A, I'm going to give you a decimal number. I'm going to ask you to write it in binary, hex, and octal. Okay. Question 1b, I'm going to give you a negative number and ask you to write it in 8-bit binary using 2's complement notation.
Just give me a canvas.
I'll put it on canvas, sure. And then part C, I'm going to give you something with numbers on both sides of the decimal point and ask you to convert that to binary. All right, that's question 1. That's 15 points. Question 2, you're going to design a circuit with 3 switches and a single LED. The circuit should light the LED when, and I've skipped the details here, but I'll tell you when the LED should be on, and then you're going to have to write a system diagram. Tell me what the inputs and outputs are, make a truth table, unsimplified sum of products, simplify it, wiring diagram. Don't worry about pin numbers and part numbers, but I want to see switches and LEDs and all the logic gates. Okay, so full wiring diagram except for pin numbers and part numbers. So that's question 2. Question 3, I'll give you a truth table. The inputs will be called ABC, the output will be called F. And I'll ask you to write an unsimplified product of sums and then write the product of sums in compact form. So that's going to be both of these notations, right? This is the unsimplified product of sums, this is the compact form. So you want to be able to do both of those. All right, part 4, going to have a 4-input function. I'll ask you to use a K-map to find a minimal sum of products for F. And this will have some don't cares as well as 1s and 0s. Okay, question 5, I'm not going to give you any hints because it's just several true-false questions. So that'll be the mystery part of the exam. Question 6, I will give you a picture of a circuit with 2 inputs X and Y and an output F, and it'll have a bunch of gates. And ultimately, I'm going to want you to come up with a simple equation for F in terms of X and Y. So write the equation, simplify it. You might want to use a truth table, but it's not necessary. And then when you have the simplified form, sketch a simplified version of the circuit. Okay, as simplified as possible. Question 7, I'll ask you to write a truth table for something that you've already worked with, and I'll describe it here. And then I'll ask you to write non-minimized sum of products for the outputs. And then I am going to ask you to do a fuse map. So this has a programmable plane over here and a programmable plane over here. And you're going to want to label your inputs and your outputs, make your fuse connections, and put an X where you want a connection, and have it implement your equation that you came up with here. That's your whole midterm. Is that helpful?
Yeah.
Okay. I can't say I'm going to do this for the final, but I can't see making it a guessing game at this point, right? If you can do all of these things with just your 2 pages of notes in 50 minutes on Thursday, right? I think we're in good shape. So that's what you want to be able to do. So prepare for that, yeah.
May I miss something? This is an open note.
You have 2 pages double-sided of notes.
Oh, okay.
So it's not your whole notebook, but you can make 2 sheets of notes that you like and bring those in with you. But then close book, close notes.
You said it was 50 minutes.
Yeah. And I'll probably start like 10 minutes after because I know some people are coming in from across campus. So we'll probably start at like 12:10 and we'll go until 1 o'clock and then we'll take a break and then come back and lecture.
Just for posterity, can it be typed up or does it have to be handwritten? The notes?
Oh, it can be anything you want. If you feel like reducing the entire textbook to 1 sheet would be helpful, you can do that. But I don't recommend it, right? Fewer notes are usually better. But yeah, if you want to computer generate them or reduce them, that's totally fine. 8.5 by 11 pages. So don't do the giant 1 sheet. All right. So the only thing in here that you haven't done a homework on yet is this fuse map, and this is a 10-point question, and that's one of 3 parts. So it's not a make or break question, but any questions on how to fill in fuse maps? Sure. So let me make a fuse map that looks something like this. So let's suppose we want to implement two functions. Let's say we want to say f equals AB or BC, and G equals AB bar or BC. All right, so we have a total of 3 inputs, A, B, and C, and a total of 2 outputs, F and G. So our inputs are up here, and you can order these however you like. And we've got a bunch of outputs available, so I'll just call this F and G. And so to generate F, I need to OR, I forgot to draw my OR gates. Yeah. So there's an OR gate down here. So to generate F, we need to OR AB with BC. And these lines here I can use to generate my different AND terms, my product terms. So we can just start at the top. Let's generate AB. So we want to take A and B and AND those together. So this top line represents AB. And we don't normally do this, but for keeping things straight, I'm just going to scribble down what min-term that, or what product term that line corresponds to. Okay, so that's AB. And we also need to generate BC. So let's pick up B and C. And the second line is going to be BC. And we also need A ANDed with B bar. So let's pick up A, and let's pick up B bar. And so this third line is AB bar. And here we need BC. Well, we could generate BC on here also, but we've also already got BC up here. So we don't need to generate it twice. We could if we wanted to, but we might just observe that we've already got a BC here. So here's one way to implement F and G. F should be the sum of AB along with BC. And G should be the sum of AB bar along with BC. There's your whole fuse map. So it's really not different from what you're doing when you draw a circuit diagram yourself using this idea of running inputs vertically coming across. It's just instead of drawing heavy dots here to make the connections and running a bunch of lines, we're using a slightly different symbology. And we just indicate connections by putting X's where these lines cross. All right, good. All right. You don't have anything due today except the lab? Okay, cool. There's a what? Oh yeah, so you had the option of turning the homework in today instead of Thursday, so turn in your homeworks if you've got them. I knew I had something I needed to grade today. Anybody else? Cool. Well, here's an inverter. We're starting to talk about sequential circuits now. So I want to start by looking a little more carefully at what an inverter actually does in the real world, as opposed to on paper. So on paper, we write a truth table, which looks like this. And according to the truth table, anytime x is 0, y should be 1, and vice versa. Now suppose we drew a graph, and we're going to show time horizontally, and we're going to show the value of x across time, and it could be either 0 or 1. So suppose x starts off at a 0, and at some point it becomes a 1, and at some other point it becomes a 0 again. Okay, let's see what y does. Theoretically, when x is 0, y is 1. And when x goes to a 1, y drops down to a 0. And when x returns to a 0, y returns to a 1. So this is the theoretical y. But here's what actually happens to y. X is 0, y starts off at 1. At this point, the input x changes from 0 volts to 5 volts. There's circuitry inside this chip that's going to cause y to drop to a 0. But that circuitry takes time to operate. It's a matter of pulling some charge out of the transistors. We talked a little about transistors. It's pulling the charge out of that gate area of the transistor so that the voltage drops down until it becomes a logic 0. And that takes time. And so this is exaggerated. This may be what happens. And when x goes from a 0 back to a 1, there may be some brief delay before the output y responds. So this is called propagation delay. And the important thing to know is that propagation delay is not 0. It's something bigger than 0. Our theoretical y, there's no delay between an input change and an output response. In an actual physical circuit, there's always some sort of delay. So here's the data sheet for our inverter. All right, there's the theoretical behavior, perfect inversion. So switching characteristics, switching means changing state, right? So here's something TPLH. So TPLH that's the propagation delay for the output to go from low to high. So the output's changing from a 0 to a 1, however much time it takes, that's what TPLH is. This propagation delay here, that's the time for the output to go from a high value to a low value. So that's TPHL. And on our data sheet, it tells us what those are. Typically, the low to high transition takes 12 nanoseconds, but it could be as bad as 22. So LH is 12 to 22 nanoseconds. And the high to low transition, TPHL, is typically 8, but no worse than 15. So 8 to 15 nanoseconds. So this could take 15 nanoseconds for the output to drop and then another 22 nanoseconds for it to rise. So worst case, 15 plus 22, 37 nanoseconds for the output to go to 0 and then back to 1. And 37 nanoseconds is a long time. Okay, a nanosecond is a billionth of a second. So if you have a 1 gigahertz clock, it's ticking up, down, up every nanosecond. And this is telling you that it would take 37 of those clock ticks to pass before our inverter's output might drop to a 0 and then go back to a 1. So if you're using this particular chip, this 74LS04, in a computer circuit, you probably can't use a 1 gigahertz clock. It's too fast. You'd have to slow your clock down to the point where you could do one of these transitions within a clock tick. Okay, so this is a long time. Now that's okay for us because mostly we've got an inverter, you flip a switch, it takes 22 nanoseconds for the LED to turn on, who cares, right? But as we start talking more about building computer circuits, right, things that have clocks and things that run continuously, you want to keep in mind this idea that there are propagation delays and we can ignore them less and less as we go forward. So this is called a timing diagram. And a timing diagram basically just shows time on the horizontal axis and then different signals, one on top of the other. Bless you. And we can use this to analyze the behavior of a circuit. And let me show you a timing diagram for a really pathological circuit. So I have X going through an inverter into an AND gate, and I also have X going directly into that same AND gate, and the output of the AND gate is Y. And I'm going to label this point right here, I'm just going to call this X2 so we can make a truth table. So X is either a 0 or a 1. X2 is going to be a 1 or a 0. And Y is X2 ANDed with X. And 0 ANDed with 1 is 0. 1 ANDed with 0 is 0. So it looks like the output Y should always be a 0 here. And if we had analyzed this using algebra, we would have said Y equals X bar ANDed with X. And I think there's a theorem we've talked about that says this is always equal to 0. Because X bar and X cannot both be true. Right? If this is a 0, this will be false, and if this is a 1, this will be false, so the AND will be false. So in theory, whatever value you put in for X, the output should always be a 0. Ignoring the fact that you'd be kind of strange if you built a circuit like this, because you just expect it to be 0. But let's look at a timing diagram for this. So here's time. And here's my input X. And I'm also going to record X2, and I'm going to record Y. And let's say X starts off at a logic 1. and then it comes down to a logic 0. Then it goes back to a logic 1. Well, we know that x2 is coming out of an inverter whose input is x. So x2 is going to start off, let me do this in a different color so we don't confuse our traces. x2 is going to start off low. And then when our input x goes low, x2 is going to go high, but it's going to take a little bit of time. There's a propagation delay. So I'll exaggerate that so it's easy to see. And then when x2 returns high again, there's going to be an exaggerated delay before x2 goes low. All right, well, y is the output of an AND gate whose inputs are x and x2. So right here, x is a 1, x2 is a 0. Our AND gate's going to be outputting a 0. We expected that. Time progresses, and here x changes to a 0. Now we've got a 0 ANDed with a 0. That's still a 0, right? So the output stays low. And here x2 rises. We've got a 1 ANDed with a 0. Y is still low. But what happens right here? They're both high. x2 is 1 and x is 1. Which means the AND gate has both inputs being 1, which means the output of the AND gate is going to go high. And there's going to be a slight delay because the AND gate has propagation delay also. So that goes high. And then over here, x2 drops to a 0, so we have a 0 and a 1 ANDed together. And so the output of the AND gate will go low after a slight delay. But this is noteworthy because there's no combination in our truth table where y should ever be equal to 1. But in fact, for a brief period of time, y is equal to 1. So this is what we call a glitch. And a glitch is an unexpected, unwanted change in an output value. Something that, according to the logical design, should not be there. But because of these real-world properties, these delays, we get this value that shouldn't appear, but it does. And if this is lighting up your LED for your traffic light, it's going to flash on for 10 nanoseconds. You're not even going to notice it. It's not a big deal. But if you have a system with memory and something is monitoring this line, and when this line goes high, it's going to do something like shut down the power to your city, that little glitch might be really important. Because 10 nanoseconds is huge to a computer. That's more than enough time to say, okay, we got a 1 on line Y, let's start the shutdown sequence. And there you go. Okay, so this is the kind of thing that crashes satellites and stuff like that. And it can be notoriously tricky to avoid these things. And it's an artifact of these real-world delays in the behavior of circuits. And we think of circuits as idealized things. This is going to be x bar, this is x, the AND is always going to be a 0, right? So when we're designing circuits, a lot of times we're using very elaborate software tools, and one of the things these tools will do is they'll analyze our circuitry for things like this, or for the potential for glitches. So the book talks a lot of detail about this. It talks about glitches and hazards. So hazards are things which indicate that a glitch might happen. And there's different kinds of hazards, and depending on the type of hazard, you may or may not be able to add more circuitry or change your circuitry to eliminate the glitch. And then you can use K-maps to identify hazards and figure out how to rectify these glitches and so on. We're not going to go into that level of detail here, okay? But glance through it in the book and at least have seen it before. but I want to go on and I want to talk about these systems with memories. So let me start this off and then we'll take a break. So I think I left you on Thursday with a pair of circuits. So did anybody think about these? During the beautiful 80-degree weekend we had. So that circuit on top, do we know what the output value is there where the question mark is?
The original value?
Yeah, I mean, it might be a 0 or it might be a 1. Suppose that it's a 0. Well, that 0 feeds the input of this inverter, and if the inverter's input is 0, the output is 1. And this inverter's input is 1, so its output is going to be 0. So there could be a 0 sitting here, and if there is, there's going to be a 0 sitting there forever. But it could also be the case that there's a 1 sitting here, 5 volts, and in that case the input to this inverter is a 1, so its output will be 0, and this inverter's input will be 0, which means its output will be a 1. So there could be a 0 or a 1 sitting at this point, we don't know, but what we know is whatever value is there, that value is going to be there forever, as long as power is applied to the circuit. So this is a form of a memory. It's remembering a 0 or a 1. And we didn't control whether that was a 0 or a 1, but in fact if you build this and you take a wire connected to 5 volts and you really briefly just tap it to that point on your circuit and then take it away, this output will go to 5 volts. And then if you take a wire and you connect it to ground and you really briefly just tap it right here, this will stay at 0 volts. So this is a really rudimentary memory. It's able to remember a single bit, but there's no easy way to sort of use this to write a 0 or a 1 into it unless we short the output to ground or short it to 5 volts and we don't burn out the circuitry. But nonetheless, it's got a memory, right? It retains a bit value. Now this circuit, on the other hand, if the output happens to be a 0, you get a 0 in this inverter, the output there is a 1, 1 in this inverter, the output's a 0, 0 in this inverter, your output's going to change to a 1. And then that 1 will come around, and this will output a 0, and this will output a 1, and this will output a 0. And so this is going to oscillate. And if you build this with 3 inverters on a proto board and you hook up an oscilloscope and you're good at looking at what's going on, you'll see an oscillating output. And the time it takes to oscillate will be 3 times the propagation delay.
Does that ever like exponentially grow when it continues to go through this, or?
No, it doesn't actually. Because this thing just sees a 0 or a 1, right? And because these are digital circuits, right, they take a range of input voltages and they say this is 1, this is 0. We don't get that kind of feedback effect. Now if this was pure analog, you probably would get what you're describing, where it starts feeding back on itself and the output gets bigger and bigger, or where it fades away. But we get a nice oscillation. Now it's pretty sloppy because it's changing as quickly as these inverters can respond to their inputs. But it's a fun thing to do anyway. And you get a couple of 100 megahertz oscillator.
So you said the first one's memory. What is that? Is that just 2 NOT gates?
Just 2 inverters connected together like that.
There's no resistors or
Nope. Just 2 inverters.
How does the memory? What does that even mean? Like It remembers what the last info was, like.
It remembers whatever the current output value is. Right? If you come over here and you measure this and you see 5 volts, you can walk away, come back an hour later, measure it, you'll still see 5 volts. But if you disconnect the power and reconnect the power and you measure it and now it happens to have 0 volts, you come back in an hour, it'll still have 0 volts.
That's just like they're connected in some little circle.
Yeah, they're just chasing their tail. But right, if a cat chases its tail clockwise, it's going to go clockwise forever. If it chases its tail counterclockwise, it's going to go counterclockwise forever. That's basically what's happening here.
Okay.
Couldn't you, get the same result with like a capacitor?
Yes. So that's the difference between static RAM and DRAM. So DRAM, the cheap stuff you get for your computer, is based on capacitors. Cache memory, the really, really, really expensive stuff inside your CPU, is based on this kind of setup. So we'll come back to that. All right, let's do a 5-minute break, and then we'll see how to make this memory useful, and that'll lead us into our next chapter.